In the consistency models we discussed so far, the memory was accessed via read and write operations only. In the weak consistency models, it's possible to have something beyond just read and write operations when memory is accessed. In the models we described so far, the underlying memory managers, or state managers in general, had to determine or infer what are important updates and then how to order and propagate the information regarding those updates. For instance, there is no way for the distributed memory managers to understand whether or not indeed the value of y was somehow computed based on this value x that was read from M1. So it's perfectly possible that P2 really just completely randomly came up with this value y that was written in M2, and that had nothing to do with this fact that it previously read the value of x from location M1, so saw this particular update. However, with the causal consistency model, it will be forced that every processor in the system has to observe that the value of the memory location M1 has been updated to X before the value of the memory location was updated to Y. However, for instance, in the same process P2, maybe at a later time, there is another update that's happening to memory location M3, and the value Z is written there. And perhaps this particular value Z was directly computed based on the value that was read from memory location 1. So there maybe is a dependence between this particular write and the value that was read here, but not between these two. How can a memory system distinguish these? To do this, the memory system introduces synchronization points. The synchronization points are operations that the underlying memory system makes available to the upper layers of the software. So in addition to being able to read and write a memory location, you'll also be able to tell the distributed shared memory sync. What a synchronization point does, it makes sure that all of the updates that have happened prior to the synchronization point will become visible at other processors. And also a synchronization point makes sure that all of the updates that have happened on other processors will become visible subsequently at this particular processor in the future. If P1 performs a synchronization operation at this particular point after this write was performed, that doesn't guarantee that P2 will see that particular update at this moment. Although this read operation is happening according to some real-time, some external observer at a later point in time than the synchronization point and the preceding write, P2 has not made an attempt to synchronize with the distributed shared memory. So P2 has no guarantees that it will see the updates performed by others. So the synchronization point, it has to be called both by the process that's performing the updates and also by the processes that want to see and want to receive a guarantee that they will see updates. However, once the synchronization operation is performed on P2, afterwards, P2 will be guaranteed that it will see all of the previous updates that have happened to any memory location in the system. So if we perform a read operation of the memory location M1 at this point in time after the synchronization, we're guaranteed that P2 will see this update. In this case, in this model, we use a single synchronization operation for all of the variables in the system, for the entire shared memory. It is possible to have solutions where different synchronization operations are associated with some subset of the state, for instance, with a granularity of individual pages. It is also possible to separate the steps when a particular process requires that all of the updates performed by other processors are visible to it. We call that the entry point, or the point when we are acquiring the updates made by others. For instance, at this particular synchronization point, we can perform an entry operation and synchronize with all the updates that were performed on others, in this case on P1. And then we can have a separate synchronization primitive. That's the exit point, or this is the point where we release to all other processes or processors the fact that we have performed certain updates. So for instance, at this synchronization point, only the updates made by P1 will be forced to other processes. The idea with these finer-grained operations or these mechanisms to really directly control what kinds of messages will be sent by the underlying state management system, by the DSM layer at a particular point of time, is to make sure that the system controls the amount of overheads that are imposed by the DSM layer. The idea is to limit the required data movement, the required messages, and coherence operations that will be exchanged among the nodes in the system. But the downside of this is that the distributed shared memory layer will have to maintain some additional state to keep track of exactly what are all the different operations that it needs to support and how it needs to behave when it sees a particular type of request. In summary, all of these models that, in addition to just pure read and write operations, introduce some types of synchronization primitives are referred to as weak consistency models, and they allow us to control the overheads of the system from one aspect. However, they introduce some additional overheads that are necessary in order to support the added operations.